And let's get back to it. This is Calculus 2. We're here to talk about sequences and series. And we're going to be talking about them for a while. We haven't even got to the series yet. That'll be in the next section. In this video, we're going to talk about limit problems and the monotone sequence theorem. We're actually going to deal with more problems at the beginning here. Look at some of these. So, theorem, common limits. Limit as n goes to infinity of natural log n over n equals 0. Well, because we just had the theorem that allows us to use L'Hopital's rule, because now we know if ln of x over x would converge to something, so would this. So basically we can just do L'Hopital's rule, which we proved for functions of real numbers, and we can apply them here. So we're going to prove some of these. I think I will probably hold off on this one. If you want to look up the proof for it, it is in the text. It is in the appendix, one of the appendices. If you want to look it up. I am going to do this one, though. This is not terribly difficult to do. In fact, we've probably done it before in class at some point. You can just apply L'Hopital's rule, since it is indeterminate, infinity over infinity. If you take derivative of the top, you get 1 over n. Derivative of the bottom is 1. It is no longer indeterminate. Top goes to 0, bottom goes to 1. This goes to 0. Pretty easy to prove. This one I find easiest to do if I rewrite it into infinity, into the 1 over n. Why is it easier that way? Well, in this form, if I write it as an exponent, I can do this trick. It's a very common trick if you want to kind of separate out what your exponent is doing from what your base is doing. You do e to the ln of your function. To the n, 1 over n. E to the ln would cancel each other out, but putting it in this form allows me to use the law of logarithms, which brings that out of logarithm. I get limit as n goes to infinity of ln of n of e to the ln of n over n. We already know that goes to 0, so from the problem 1, so this goes to e to the 0, which is just 1. The only thing mysterious about this is that, as n goes to infinity, but the exponent is going to 0, so the question is which would win. Would it go to 1 or would it go to infinity? Because, you raise something to the 0 power, it's going to be 1. You raise something to infinity, it's going to be infinity. So this tells you going to 0, 1, and it became just 1. I think it'll be similar for this one. Although I don't even really think it's that important. This is just, if x is just some number other than 1, if the exponent goes to 0, that's pretty simple. X to the 1 over n just goes to x over x to the 0 as n goes to infinity. Which, that's just 1. So there's not even really much of a trick to that one. Why is this one? Well, notice this is saying for absolute value of x less than 1. Well, that means if it's less than 1, that means this is like 0.9 or 0.8 or 1/2. And if you take 1/2 to the n as n goes to infinity, well, every time you raise this to a higher exponent, it's going to go towards 0. And it's true if it's negative as well. But if it's between -1 and +1, as n goes to infinity and its exponent, it's going to get closer and closer to 0. So that's why this is true. If you want to actually do a proof of it, I guess you just have to show it's decreasing. This one you can use logarithms as well. This is kind of a neat one, by the way. You wouldn't necessarily think this would be true. E to the x is just equal a infinite limit. But you can use our logarithm trick again. This is limit as n goes to infinity of e to the ln of 1 plus x over n to the n. So that's going to be limit as n goes to infinity of e to the n ln 1 plus x over n Well, we're really only curious about the exponent there. It's not indeterminate right now because it's a multiplication, but you can rewrite it as a division. 1 plus x over n over 1 over n. Technically it's e to this, but the e doesn't really matter until I actually get what this exponent goes to. So if you do L'Hopital's rule, that will be 1 over, let's see, take derivative in terms of n, that would be 1 plus x over n times the exponent, which would be negative 2x, negative x over n squared. And then all of that over negative 1 over n squared. So you can basically cancel out the negative n squared part. And now you've got x over 1 plus x over n. Multiply top and bottom by... Well, honestly, I'll just leave it like that. That's not indeterminate as it sits, because the top goes to x, bottom goes to 1, as x over n will go to 0 as n goes to infinity. That just goes to x. So this whole thing then has to go to e to the x. The only thing I'll point out on this one, because I'm not going to show the proof of it, but you may or may not be familiar with the factorial notation. It was brought up in section 8-9, the probability section in our textbook, which, depending upon our semester, I might not have covered in this set of videos. So in factorial, the way you calculate it, it's only good for integers, positive integers, natural numbers. So like 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. It just multiplies by every number decrementing down to 1. It is true that 0 factorial is actually defined to be 1 as well. That's just a fringe case. Might come up now and then. If it does, that's how it's defined. Let's do some limit problems. These are all from our textbook in section 10.1. This first one is problem 34. We're trying to determine whether it converges or diverges and find its limit if it does converge. This one's a pretty simple one. The limit as n goes to infinity of this thing. So you got 1 minus n cubed over 70 minus 4n squared. You can do L'Hopital's rule if you want, or, I mean, you could do the old trick of dividing top and bottom by the highest power on the bottom. Either way. Or you could just recognize from doing this work what's going to happen, really. 1 over n squared minus n over, let's see, 70 over n squared minus 4. So, top's going to negative infinity, bottom's going to negative 4, so this is going to positive infinity. And you get a similar result if you did L'Hopital's rule. You do 2 derivatives and it won't be indeterminate anymore. 2 derivatives you'll have, let's see, first derivative you get rid of the... Well, you won't have to really even do more than 1 derivative. Do 1 derivative, you get negative 3n squared over negative 8n. And at that point, that's 3/8 n. Limit as n goes to infinity of that is infinity. So there you go. It's pretty quick. This one diverges to infinity. Let's look at this one. We look at the limit as n goes to infinity of this baby. N pi cosine of n pi. Well, the thing about this one is this oscillates infinitely between, I guess we could even be specific, at 0 it's 1, at pi it's negative 1. Yeah, it just oscillates 1, negative 1, 1, negative 1, etc. And then this is going to infinity. So we've got infinity times an infinitely oscillating between 1 and negative 1. This diverges. And we can't even say it diverges to infinity or negative infinity because it really flips between them with every n. This is another one we looked at before that you can use your logarithm trick. N goes to infinity of n plus 4 to the 1 over n plus 4. We use our logarithm trick. Limit n goes to infinity e to the ln of n plus 4 to the 1 over n plus 4. So that's the limit as n goes to infinity e to the ln of n plus 4 over n plus 4. And we've actually already seen that basically from our theorem with our common limits. We know this goes to 0 because n plus 4 goes to infinity faster than ln of n plus 4. So this is going to go to e to the 0, which is 1. This is going to take a little bit more thought involved in it. But let's investigate what this looks like. You know, this is n times n minus 1 times n minus 2 times n minus 3 times dot 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 times 3 times 2 times 1. And then, so we have n of these. And then we have n, etc. n. Well, note, the top is increasing towards n. So basically, if I broke it up into fractions like this, every one of these, except this one, would be less than 1. It would be a fraction, like 2/3, 3/4, 4/5, that kind of thing. And if you multiply that by that, it makes the function smaller. So we're actually going to do a little trick here. We're just going to say this is less than or equal to 1 over n. How is that helpful? Well, we know limit as n goes to infinity of 1 over n is 0. And if you think about this then, 0 is less than or equal to n factorial over n to the n is less than or equal to 1 over n. The limit as n goes to infinity of 1 over n equals the limit as n goes to infinity of 0 equals 0. So, the limit of this thing has to equal 0 as well. Limit as n goes to infinity of n factorial over n to the n has to equal 0 by the sandwich theorem. If ever you can bound your sequence by a sequence that's going to 0, your sequence has to go to 0 as well by the sandwich theorem. It's a nice result you can use a lot. Alright, let's look at this problem. So, if you think about what's happening in the top, you've got n times n minus 1 times n minus 2, dot dot dot, times 3 times 2 times 1. And on the bottom, well, I think a good way to organize it would be think about it like this, 10 to the 6th to the n. So under each one would be a 10 to the 6th. Now, the thing is, it's going to take, 10 to the 6th is a big number. That's 1,000,000. So, it'll take quite a while, but eventually you'll get a term where the top will be larger than 10 to the 6th. You have to go out to 1,000,000 factorial, but eventually, n will be larger than 1,000,000. And because of that, then you'll start multiplying by numbers bigger than 1. And that will increase infinitely. So at that point, it will start to diverge to infinity. It's going to go to 0 first, though, because it's going to take a very long time before it will actually get a large enough numerator to start increasing. So how do we indicate that? Well, let's see here. We know at a certain point for n greater than 10 to the 6th, we know then the top will be n times n minus 1 times n minus 2 times dot dot dot. I'm just going to say 10 to the 6th factorial over, let's see, this will be 10 to the 6th to the 10 to the 6th. And then we will have, see how many will we have left here? We will have 10 to the 6th to the n minus 10 to the 6th. Alright, so this we can just separate out as a constant. I'll call this C. So C equals 10 to the 6th factorial over 10 to the 6th to the 10 to the 6th. Alright, if we look then at that function, n times n minus 1 times n minus 2, n minus 3, down to basically 10 to the 6th plus 1 to over 10 to the 6th to the n minus 10 to the 6th. So, in essence, we have here then n over 10 to the 6th, n minus 2 over 10 to the 6th, n minus 3 over 10 to the 6th, dot, 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 dot. And then we have, 10 to the 6th plus 1 over 10 to the 6th. So we have n of these, we have n minus 10 to the 6th. Of these fractions, and if we just compare them to, let's see, what's probably the easiest way of doing it? If I make, that's making it larger, all of these make it larger, so this is greater than n over 10 to the 6th, and then this goes to infinity, so this has to go to infinity as well. So, because this goes to infinity, this part goes to infinity, this part goes to a constant, they both go to infinity. Infinity times a constant is still infinite. A few more examples to go. Let's look at this one. 3 to the n, 6 to the n. Well, the main thing here is that I can put that 2 to the n up top. That becomes 2 to the n times 3 to the n times 6 to the n over n factorial, which I guess would be 6 to the n times 6 to the n, or 6 squared, so 36 to the n. 36 to the n over n factorial. Basically the same idea as before when we were looking at this thing. Yeah. Same argument as the last one. By same argument. Well, actually, the n was on the top in that one, wasn't it? Certainly that's, yeah, the n was on the top in that one. This one, the n is on the bottom, so this is going to go to 0. So by same argument, this equals 0. And to show it, I mean, you could just do the n times n minus 1 times n minus 2 dot, dot, 2 times 1. On the top you got 36, 36, 36, 36, 36. So, I mean, this would be, if I make the bottom smaller, yeah, it's less than 36 over n, which that goes to 0, so that goes to 0. This is an indeterminate form that's a subtraction. So it's not something we can do L'Hopital's rule on as it sits, But we can do some work on it and make it into something we can do L'Hopital's rule with. Because if I take the limit as n goes to infinity, it is infinity minus infinity. Kind of minus an infinity, so what's going to happen? Well, you can rationalize the denominator by doing this trick. Multiplying top and bottom by n, the conjugate, by the conjugate. N squared minus n over n plus square root of n squared minus n. And this gets you n squared minus n squared minus n, in parentheses, over n plus square root n squared minus n. And then that's going to be n over n plus square root n squared minus n. And at that point you can either do L'Hopital's rule or you can do the division trick. I think I'm going to do the division trick, divide top and bottom by n. That'll get me 1 over 1 plus square root of. Take it inside the root. You get inside the root will become n squared, so n squared divided by n squared is 1, and then n divided by n squared is 1 over n. So this is going to become 1 over 1 plus 1. Yeah, because 1 over n will go to 0, so 1 over 1 plus square root 1 is 1/2. So yeah, that subtraction goes to 1/2. N goes to infinity. Alright, for our last problem we're going to look at before we go look at some theorems and get done with this section. This is a recursive problem. So let's look at this for a bit. Instruction is to find the limit. I tried to find this in a straightforward way. I failed miserably. I looked up the solution, and they suggested, since the problem says assume that the sequence converges, you can kind of trick it. Because you can say, okay, limit as n goes to infinity of a sub n equals L. So that means the limit of a sub n, limit as, n goes to infinity of a sub n is the same as the limit as n goes to infinity of a sub n plus 1. You're just skipping the first term. So with that in mind, limit as n goes to infinity of a sub n plus 6 over a sub n plus 2 equals L plus 6 over L plus 2, and that equals the limit equals L. So since that's true, you can basically just solve the equation. L plus 6 equals L squared plus 2L. So 0 equals L squared plus L minus 6. So L plus 3, L minus 2 equals 0. L equals negative 3 or positive 2. There is no possibility of it being the negative one, just from the work we were doing because of the addition, so it is 2. To finish out this chapter, we're going to talk about a couple definitions and then a theorem. So here's definition. A sequence is bounded from above if there is some number m such that your sequence values are all less than that number for all n, for every index. And you call m an upper bound in that case. If there is no upper bound that is less than m, then m is called the least upper bound. Similarly for bounded from below, greatest lower bound. It's basically the same thing, it's just you have something bounding the bottom of it instead of the top of it. If a sequence then is bounded both above and below, we call it a bounded sequence. And if it lacks either bound, an upper or a lower, we call it unbounded. A sequence is non-decreasing if each subsequent term is greater than or equal to the previous term. a sequence is non-increasing if each subsequent term is less than or equal the previous term. So a sub n plus 1 is smaller than or equal to a sub n. Then we call a sequence monotonic if it's one or the other. So if it's basically always increasing or remaining constant, or always decreasing and remaining constant. Either or, not at the same time. Mainly because it's impossible to be doing both at the same time. So here's the theorem. It's a very important theorem. It kind of gets you a lot of nice results, but it's a fairly simple statement. It just says if a sequence is bounded and monotonic, then it must converge. I'm not actually going to present the proof of this one. It is in the textbook. It's a neat little proof. It's mainly graphical. It's in page 580 and 581. But it's just a deceptively simple theorem. It just says all you have to do is establish that the sequence is bounded and it's either always decreasing or always increasing. If so, it must converge. And it actually converges to either its upper or lower bound, depending upon whether it's decreasing or increasing. That'll be it for this section, for this discussion of sequences. Next time we will move on to talk about series, which are related, but are a different thing. A lot of people in common English will use both words to mean the same thing, but in mathematics, they are different. So, see you in that video. Have a great day.